Hello students, in today's session we are going to learn round robin scheduling. Round robin scheduling works by defining a time quantum for every process. So whatever process is inside a ready queue, so it will allot a time quantum for every process. So every process will be executed for that particular time quantum. So it is similar to first come first served scheduling algorithm with the additional thing is that it has the time quantum. So obviously, since it allots predefined time quantum, there will be preemption. Okay, so there will be a context switching from one process to another process, because once the time quantum expires, so the CPU will be moved from it will be released from one process and then it will be allocated to another process. So here the ready queue will be treated as a circular queue, because the time quantum will be allotted same amount of time period will be allotted for every process. So once say for example, if time quantum is 4 milliseconds, so the first process will be executed for 4 milliseconds, then the CPU will be allotted to next process, then the next process will execute for another 4 milliseconds, then from that process it will move to the third process. So likewise it will be moving around the process in a circular fashion. So that's why the ready queue will be treated as a circular queue here. So the CPU scheduler will go around the circular ready queue in a circular as a circular queue, and then it will allot the CPU to each process for a particular time quantum. So how does the CPU scheduler execute the process? So it will pick up the first process in the ready queue, then sets the timer to interrupt after the time quantum expires. Okay, and then it will be dispatching the process to the CPU. So this is what happens for every process. Picks up the first process, sets the time, then dispatches the process for execution. Once the time expires, then moves to picks up the second process. Okay, so this continues until all process completes its execution. So here there are two cases that comes into existence, where based on the time quantum. Okay, so if the time quantum is if a process has a CPU burst time which is less than the time quantum, then the process itself will release the CPU. Okay, say for example, the CPU burst of a process P1 is 3 milliseconds, whereas the time quantum is 4 milliseconds. Then obviously the burst time is less than the time quantum, so the process P1 will complete before the time quantum expires. So in this case, the process itself will release the CPU, so that CPU will be allotted to the next process. So if it is the other case, that is if the CPU burst is greater than the time quantum, then the timer once the time quantum expires, it will cause an interrupt to the operating system, so that there will be a context switching that will take place, so that the CPU will be released from the current process and then allotted to the next process in the ready queue. Then again it will, in a circular fashion, again it will move come back to the current process. So let us look into an example, so that you will have a clear idea about this scheduling algorithm. So consider these three processes, P1, P2 and P3. P1 having CPU burst time of 24 milliseconds, P2 with 3 milliseconds and P3 with 3 milliseconds. So now let me explain you about the Gantt chart, how the process will be executed if the time quantum is 4 milliseconds. Okay, so you will be given the time quantum. So you will be given the set of process and their burst time along with the time quantum. Okay, so with these details you have to you have to draw the Gantt chart with which you will be able to find out the waiting time and turnaround time of each process, and finally the average waiting time and average turnaround time of a process. So let me explain you the Gantt chart. So since round robin scheduling is similar to FCFS with additional time quantum, so first the process P1 starts its execution. Look into the burst time of the process P1. So it is 24 milliseconds, but the time quantum is only 4 milliseconds. Okay, so P1 starts its P1 will be started first, which will be executing for 4 milliseconds. That is for the defined time quantum. Then it will be moving to the process P2. Okay, so if you look at the process P2 here, the burst time is only 3 milliseconds, which is less than the time quantum. So it completes its execution before the time quantum expires. So now it voluntarily releases the CPU so that P3 gets the CPU. So now again P3 has its burst time, which is less than time quantum. So it takes its own time and it completes its execution. Okay. So now only P1 is remaining. Okay. So P1 has completed 4 milliseconds. So remaining 20 milliseconds are there. So until P1 completes, the CPU will be allotted to process P1 alone. See, P1 11 to 14 milliseconds. Then again, since there are no other process in the ready queue, CPU will be allotted to same process P1. Okay, so 15 to 18, and then again 19 to 22, then again 23 to 26. Sorry, not 26, it is 24. Okay, so because only 24 so 22 to 26 it takes, so totally the execution time is 24 milliseconds. Okay, if you count from here, so 0 to 4, so it starts from time 0, so 4 milliseconds it takes first, then again if you start at 11th millisecond, so 11 to 14, so again another 4, so 8, then again another 4 here. So for P1, so this is the first 4 milliseconds, then the next 4 milliseconds, and then the next 4, so 12 milliseconds, then again the another 4, so it is 16 milliseconds, then again the next 4 it is 20 milliseconds, then again another 4, so 24 milliseconds. Okay, so in this fashion the CPU will be allotted to process P1 until it completes its execution. Okay, so in terms of the predefined time quantum, so 4 milliseconds, 4 milliseconds, so like that. See how many, so 6 times the CPU has allotted the time quantum for same process. Okay, so if you calculate the waiting time for these 3 processes, so let us consider the process P1 first. Okay, so at first it has not waited for any time, so immediately process P1 has started. So initially it is 0, but when you since it has not completed its execution, it waits till this 10 milliseconds. Okay, so 10 minus this 4. Okay, so 10 minus this 4 milliseconds, so totally will be having 6 milliseconds. Okay, so the P1 waits 6 milliseconds for completing its execution. Okay, total waiting time is 6 milliseconds. So after 10th millisecond, P1 itself has got the CPU and it continues its execution until it completes. So what about P1's turnaround time? So the turnaround time is 30 milliseconds. That is the total time taken for completion. Okay, so it is 30 milliseconds. But for P2 and P3, so let us calculate the waiting time for P2 first. So for P2, the execution has started from the fifth millisecond. Okay, 5, 6 and 7. Okay, so it has waited up to 4th millisecond. So the waiting time for P2 is 4 and the turnaround time, that is total completion time, is 7 milliseconds. Okay, then for process P3, so P3 has waited until 7 milliseconds and got its turn to CPU, and then it has completed its execution at 10th millisecond. Okay, so the waiting time for process P3 is 7 milliseconds and turnaround time is 10 milliseconds. So if you calculate the average waiting time and average turnaround time, so the total waiting time is 17 milliseconds. 17 by 3, you will be getting 5.66 milliseconds. Then the total turnaround time is, so 30 plus 7, 37, then plus 10, so 47. So 47 is the total turnaround time. Average is 47 by 3, is 15.66 milliseconds. So I think you could have understood the working procedure of round robin scheduling. So it is mainly based on the time quantum. So if the time quantum is less, then the context switching will be happening very often. So this picture explains you about the frequency of context switching based on the time quantum. So if the time quantum is 12, it is for one process. Okay, so if the process is if the processing time or CPU burst time is 10 milliseconds, then the time quantum is 12 milliseconds, and here no context switch occurs because before the time quantum expires, the process has completed its execution because the burst time is 10 milliseconds. If the time quantum is 6, is set as 6 milliseconds for the same process, then one context switch will happen because the process will execute for 6 milliseconds. Then again it will move to some other process. Then once the process gets its turn, then it completes its remaining execution time. Okay, so at least one time context switch will occur. Okay, whereas if the time quantum is set as 1 millisecond, then see, so totally 9 times the context switching will occur. Okay, switching context switch means that the number of times the CPU has been released from the one process and then allotted to the next process. Okay, since the time quantum is 1 milliseconds, the CPU burst time is 10 milliseconds. So for every 1 millisecond, it will be moving to some other process until the burst time completes. Okay, so the so you have to choose the appropriate time quantum so that it will reduce the number of context switches. I hope this video will be very much useful for you. In the next video, I will explain you how priority scheduling algorithm works with a simple example. Thank you.